Hello guys, my name is Jason and today we're going to be talking, wait, y'all hear that? In today's video, we're going to be talking about nuclear chemistry and radioactivity. We're going to be hitting a few points like the types of radioactivity, the value of stability, equations, half-life, fission and fusion, and more. So let's get right into it. Before we go further along in today's topic, we have to ask ourselves, what is nuclear chemistry? If you read on the board, it says nuclear chemistry is a branch of chemistry that deals with the study of nuclear reactions and processes involving atomic nuclei. This means it isn't just destruction like I did for my intro or the picture on the right. It involves nuclear chemistry, but nuclear chemistry can actually benefit us in many other ways, and we want to learn and understand why it can be dangerous and why it can be useful. Now, for the basis of nuclear chemistry, we're going to be looking at four different kinds of radioactivity. The first one is alpha decay. This occurs when an unstable nucleus emits a particle composed of 2 protons and 2 neutrons. If we look at it, it has a molar mass of 4 and a 2 on the bottom to state its protons, and it has an element of helium. If we look at the top right as an example, on our left we have the parent nuclide, or also as our reactant, uranium. It has a molar mass of 238 with a number of protons as 92. On the right, on the product side, we can see that we have 234 over 90 for our protons and molar mass, and we also have helium with 4 molar mass and 2 protons, which states that it spitted out this alpha decay. For beta decay, this occurs when it is an unstable nucleus that emits an electron. This also kind of spits it out, but instead it emits an electron. For this, we would be using 0 over negative 1 E. And E doesn't stand for an element, it just stands for an electron. Now, for gamma emission, it is a form of electromagnetic radiation. When a gamma ray photon is emitted from a radioactive atom, it does not change the mass number nor the atomic number / proton, but it also does work in different ways. Gamma rays are high energy, short wavelength photons. They have the lowest ionizing power but the highest penetrating power. This is why it is used in medical fields, x-rays, for cancer, and this is why it can be such a useful thing but also dangerous. Now, our last ones are positron emission and electron capture. These kind of work like polar opposites. Positron is an unstable nucleus that emits a positron. It has the equation of 0 over positive 1 E, which is an electron. Electron capture involves a particle being absorbed by rather than emitting from an unstable nucleus. Basically just the opposite, and instead it's capturing this electron. And with this, we're going to be able to move on to the value of stability. Now that we've looked at the four kinds of radioactivity, we have to understand, why do certain nuclides go through these things? This is where the value of stability comes into play. If we look at the bottom right, we see even, odd, even, odd. We can see the number of nuclides that would be created with this ratio. This ratio is neutrons to protons. We have to see if there's an even amount from protons to neutrons, and if there isn't, there's a lower chance of nuclides. This is where kind of a weird play comes in, and it's called magic numbers. The magic numbers would be 2, 8, 20, 28, 50, 82, and for neutrons, 126. These can make the nuclide more stable, but it wouldn't guarantee stability, and you have to make sure to remember about that. If the nuclide is too high in the ratio, that means it has too many neutrons. The neutrons will convert to protons using beta decay. And on the other hand, if the nuclide is too low, that means there's too many protons, in which the protons would convert to neutrons. The value of stability is just a graph in which we utilize our proton to neutrons to see where it would be placed on a graph. If we would have to utilize beta decay or alpha decay to get back on the valley of stability, in which our nuclide will finally be stable and not radioactive. Now that we have reached half-life and kinetics of radioactive decay, we had to see, how does this work together? Well, we know that half-life is the time it takes for exactly 1/2 of our sample to decay. If we look at the first equation, it is one of the equations for kinetics of radioactive decay. but actually it is the exact same equation as the one on the bottom. We have natural log final nucleotides over initial nucleotides. The final is just half of the initial. So if our initial was 2, then our half would be 1. So it's 1 over 2. This would equal negative rate constant time. If you are able to solve this problem out, you would actually get t1/2 equals 0.693 over k, which is just half-life. Also, as well, if we look at the right side of the graph, we can tell that at 100 seconds, we have reached the half-life of 0.1, which is 0.05. This is all interconnected because we understand that radioactive decay is all first order. We don't have to worry about different formulas like second order or zero order, which makes our life a whole lot easier just by understanding that radioactive decay is first order. In our final part for the nuclear chemistry, we're going to be looking at fission and fusion. Fission is a reaction in which the nucleus of an atom splits into 2 or more smaller nuclei. If we look at the bottom left, we see one nucleus being split into 2 nuclei with some neutrons on the side. On the opposite hand, we have fusion. An atomic nuclei of a low atomic number fuse to form a heavier nucleus with the release of energy. This basically means 2 becoming 1 with the release of energy as well. While these two things are there, the one that is more common is fission. We use this for energy, and we use this for the nuclear bombs, the atomic bombs, and that's how it works. Fusion, on the other hand, is a lot harder. Where we see fusion naturally is the stars in the sun, but creating and making fusion from man-made is actually really hard. Fusion is so strong that it is 3 to 4 times stronger than fission energy alone, because it is trying to match the energy that the sun emits, which is why it's super hard for fission to be created. Now that we have learned all about nuclear chemistry, we can see why it is so important and how it can be applied in our lives. On the left, we can see that the nuclear power plant, which utilizes fission, like I've stated, makes up for 20% of the United States energy. In the middle, we see a PET scan, which is used to evaluate organs or tissues to see the presence of diseases or other conditions, which can save your life. This utilizes gamma, which is part of one of the radioactive decays. And on the right is one of the downsides to nuclear chemistry, which are nuclear weapons, which have been used in the past but are banned. This can cause great chaos, problems, and danger, but we still have our benefits from nuclear chemistry.